All right, back to thermodynamics 2 homework. This is homework number 2, which is Clapeyron problems and Gibbs free energy / equilibrium problems. So this number 5 is find the triple point of a certain pure species from the following information. The substance sublimes at these conditions, it boils at these conditions, the heat of sublimation is this, the heat of vaporization is that. Okay. Blah, 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 blah. Okay, what's the first thing I do in these problems? I recognize it as a Clapeyron problem. What are some of the key words? Well, I got phase changes, I got sublimations, I got boiling, I've got triple points. That's all phase changing nonsense. Okay, now this one's a little goofier, but what do I do whenever I have a whenever I do a Clapeyron problem, not a triple point? I write down the Clapeyron equation. dP dt equals H alpha minus H beta over T V alpha minus V beta. And you are not expected to memorize that one. You can have that written down. You can have it on your cheat sheet. That's fine. It's simplifying it that I want you to be able to do on your own. Okay. Now it's trying to find the triple point. Okay. So what is the triple point defined as? Well, the triple point is defined as where I have 3 phases: solid, liquid, and vapor. Okay. And if I think about a PT diagram, so PT, I have the, vapor, liquid, and then, solid. Okay. Oh. Solid. Okay. And the triple point being right there. Okay. Now, looking at the problem, I'm trying to find where that point is. And like every other Clapeyron problem, I usually have some reference point. For example, I know the boiling point at, I know what temperature something boils at atmospheric conditions, but if I increase the pressure, what's the new boiling point? Okay. Or I know this freezes at this thing. Okay. So here it's saying I know where it boils, and well, when something boils, it goes to which phase? Yeah, it goes from liquid to vapor, so it's somewhere along this line. Okay. I also have sublimates. Okay. So what is sublimating? When I'm going from a vapor to a solid without going through the liquid phase. So I'm actually talking about this region right there. Okay. Well, what do you notice about this line and the triple point? It's where they meet, right? It's where they intersect. I have 2 lines and they intersect at the triple point. Because let's face it, at the triple point, things are sublimating at the same time that they're boiling. Okay, because I have all 3 phases. Now, yes, I could use stuff about melting too if I wanted. But the math is harder. Okay. And so, I'm trying to find out where this relationship for sublimating equals this relationship for boiling. Okay. So I need to solve that relationship for both. Okay. So let's do that. Now, how we want to go about this is wherever they share the math, do the math. You don't have to write the math twice. Just write the math once. But as soon as the math deviates, that's when I want you to do something different. Okay. But I do want separate assumptions so that I know where the math is deviating. Okay. So let's think about the assumptions on case 1, boiling. Okay. So, what are the assumptions I can have? Okay. I have my 4 assumptions, okay, that I can possibly have. One of them is that delta V is constant. Okay. Now, is delta V constant? Well, let's assume we're doing boiling. Okay, so we're doing the boiling assumptions. Okay, is the change in volume from a liquid to a vapor constant with changing temperatures and pressures? No, not even close. Why? Because there's a vapor. Okay. And if I think about the sublimation case, it's the same thing. That one's also not valid because I'm going from a solid to a vapor. If I have a vapor, that cannot be valid. Okay, so that's a no-go. Okay, another assumption is that the delta H is constant. Constant with delta T and delta P. Okay. So let's look at the boiling case. So first off, when can I assume that that's true? When delta T and delta P are relatively small. Let's look at the problem. Okay, I don't really know where the triple point is. Okay, so maybe after the problem's done and I get a triple point, I'm like, that's a pretty big change in temperature. That's a pretty big change in pressure. Maybe I have to go back and really assess my assumptions. Okay, that's very possible. But we might have to assume they are because it says heat of vaporization is this. It doesn't give me an equation. It says it's 27. So even if it is not constant, we have to assume it's constant. Okay. But, assuming that the temperature is between the boiling point and the sublimation point, well, that's a difference of 75 K. That's not huge. Okay, it's not small, but it's not huge. And the pressure is pretty much the same. So really, that's probably a pretty good assumption. Okay, and the same thing here. So this is vape, this is sub, and for the same reason, the delta T is pretty small and the delta P is pretty small. Okay, so those are both kosher. Okay. All right. What other assumption do I like to make? Oh, I like to make that V alpha is much, much bigger than V beta. Well, so in this case, alpha is my vapor, beta is my liquid. Is the vapor phase much, much bigger than the volume of the liquid phase? Yeah! Huge! Orders of magnitude. Okay, what about over here? Oh, assumption 1. Assumption 2. Assumption 2. Is V alpha much, much bigger than V beta? Is the volume of a vapor much, much bigger than the volume of a solid? Yeah! It's huge! It's the same kind of thing. So yeah, they're both valid in both cases. Okay. And then the last thing I like to assume, and what we always love to assume. We love to assume an ideal gas. Okay, and so when is the assumption of an ideal gas valid? Yes, when I don't give you an equation of state, yes, you've got to assume it's valid. That's true from a meta point of view. But from an engineering point of view, when is it valid? At high temperatures and low pressures. Okay. High temperature, yeah, not exactly. So that might not be a good assumption because I'm pretty low temperature. Okay. Depends upon what it is, but it's pretty low temperature. What about pressure though? Those are really low pressures. 0.2 bar, 0.5 bar. Temperature-wise, I might not be much of an ideal gas, but my pressure, that easily can make it an ideal gas. So we're going to say it's an ideal gas in conjunction with the fact that also I'm not given an equation of state. But even if I was doing this from a real analysis point of view, like I didn't want to you know, I don't want to try and find the triple point, you know, like of a substance, but I know the sublimation point and I know the boiling point. Well, I can use this to estimate it. Okay, and these and like I've said, these two kind of cancel each other out. Okay, so they both have the same exact assumptions actually, but on your homework I want you to list both assumptions. Okay, so let's just do the math. And when they deviate, because they're going to have different delta H's and stuff, but let's just assume it's just delta H for now. We'll just do the math for one of these. Okay. And, well, what do you notice about these three assumptions? They're the same exact ones for Clausius Clapeyron. Okay. So I know what my endpoint is, but I don't care. You don't go just straight to Clausius Clapeyron. You derive it every single time so you can practice applying these assumptions. Okay, and so let's do that. Okay, so first thing I do is I separate and I integrate. I separate and quote-unquote integrate, but I'm not actually going to integrate yet. Okay, so I got dP is equal to delta H, and it could be sublimation or boiling, okay, or vaporization. T V alpha minus V beta dt. Okay. Well, first off, I know that this is 0 in both cases because of assumption number 2. I know that this is constant because of assumption number 1, which allows me to pull it out of the integral. And assumption number 3, what does assumption number 3 let me do? It lets me plug in the ideal gas law, which is V equals RT over P. Okay, and so this becomes V over RT over P. Assumption number 3. Assumption number 1. And then doing some rearrangement of the math, I'm going to get that dP over P is equal to delta H over R dt over T squared. Yeah. And it's okay to skip that. Now you might be like, well, what are my bounds? Well, technically, your bounds are, you know, your pressure that your reference point is to your triple point pressure. Problem is, I have both a pressure and a temperature that I don't know. So instead of solving this as a definite integral, we're going to solve this as an indefinite integral. Okay. Which means that this becomes natural log of P equals minus delta H over R T plus C. Some constant. Okay. And this is where the math needs to deviate. So this is where my math starts to deviate, because my constant is going to be different whether I'm boiling or whether I'm sublimating. Okay. So let's first solve for the constant on one, and then we'll solve for the constant on the other. I mean, I can still do the algebra to solve, quote-unquote, for the constant. Okay. What is the constant? Well, the constant, whatever it is equal to natural log of P plus delta H of whatever it is, R over T. Okay. So, C sublimation is equal to the natural log of P sublimation plus the delta H of sublimation over R T of sublimation. Okay. Plug and chug. I have no idea what it is, and like I said, I'm never going to plug in a number down here. Okay. And I do the same thing for vaporization. C of vaporization is equal to natural log of P vape plus delta H vape over RT vape, or boiling. Again, plug and chug. All right. Make sure you watch your units, make sure you are using Kelvin and all that good nonsense. Okay. So now that I have the constants, okay. Well, that still doesn't tell me the triple point. All right. Well, I can do, and if I did this as a definite integral, I'd still have like those two unknowns. but I have two equations, so it's okay. So what I can do, because at the triple point, I am sublimating and vaporizing at the same time. Meaning, at the triple point, the sublimation pressure is equal to the vaporization pressure. And the boiling point is the same as the sublimation temperature. Okay? And so, I can set them equal to each other. And really, it's that equation that I just erased that I want to set equal to each other. So that the natural log of P sub is equal to the natural log of P vape, which says that C sub minus delta H sub over RT sub is equal to C vape minus delta H vape over R. Well, is this still T sub? No, because P sub is equal to P vape at the triple point. Okay, so those are actually the same temperatures. So that's actually what I'm solving for. I'm solving for that temperature. Okay, because I know everything else. I just need to plug them in. Okay, so I do some rearrangement. Okay, so I have C sub minus C vape. I've got, well, they have the same thing, so I have delta H sub minus delta H vape all over RT triple. So rearrange things. So T triple is equal to delta H sub minus delta H vape all over R times C sub minus C vape. Plug and or chug. Well, that's the temperature. Is that the triple point? No, because I also need to know the pressure. Well, where do I get the pressure? Well, I just plug it back in. I plug it back into this guy. So, I can say that the natural log of P triple is equal to the minus delta H of vaporization over RT triple, which I've already solved for, plus C vaporization, which I've solved for. Plug and or chug, there's my answers. There's my triple point. So again, the Clausius-Clapeyron aspect of this is no different. The only thing that's tricky about this problem is that I have this setting them equal to each other.